Okay, hello everybody. So here is the quicker version for subtopic 9.2, radioactivity. So basically radioactivity is disintegration of unstable nucleus to a more stable daughter nuclide with the emission of alpha, beta and gamma particle. Okay, so basically radioactivity tells us about how the parent nuclei will change to a daughter nuclei from unstable nucleus to become more stable. Okay, so here we have a graph of nuclei sample, okay, that undergoes radioactivity decay. Okay, so because it is decaying, that's why the graph is decreasing. Okay, so the equations involved for the subtopic is from equation 87 until the last equation 91. Okay, so in this video I will only be focusing on the usage of the equations. Alright, so for 87 we have the equation for the law of radioactivity decay, which is dN over dt. We call it the decay rate is equals to negative lambda n. So negative here tells that the sample is decreasing, hence the negative sign. And then we have lambda. So be careful in this topic. Lambda means decay constant. Okay, and then n is the number of the sample exists. Alright, and then we have equation 88 where we have n equals to n naught exponent negative lambda t. So n naught is the initial sample, okay, the starting before the decay happens, and n here is the remaining sample after a certain time, okay, that correspond to this time here. Okay, and then we have lambda, decay constant, right? And for equation 89, which is almost similar to equation 88, where we have A equals to A naught exponent negative lambda t. So A is what we call as activity. Okay, so A is simply after decay process, and A naught is the initial activity. Okay, so the unit for activity is in becquerel. Okay, or the SI unit is in per second. Okay, so usually we'll use becquerel, but there is also another unit for activity which is called curie. So if the question gives you in curie, you must convert it into becquerel first, because becquerel is the SI unit. Alright, next we have equation 90, where equation 90 is A equals to lambda n, activity A equals to decay constant lambda times with the number of sample n. Okay, number of the nuclei exists. Right, so if you compare between equation 87 and 90, okay, you will notice that these two equations is almost similar except for the negative sign, okay, indicating that it is decreasing as I mentioned just now. So in other words, we can say that A is directly proportional to the number of nuclei. The activity is directly proportional to number of nuclei. That is why we have equation 88 and 89 being almost similar. Right, just to emphasize the usage of equation 90, where this decay constant here, lambda, must be in per second. Okay, it cannot be in other unit. For example, like per minute or per days or per year. Okay, it must be in per second. Why is that? If we look at equation number 91, where we have T half. T half is called half-life, okay, which is related to ln 2 over lambda. So lambda here is the decay constant, but our T half, okay, which is half-life, can exist in days, hours, minutes or seconds. Okay, so in other words, since decay constant is related with half-life, okay, therefore decay constant can also be in per days, per hours, per minutes or per seconds. However, if we want to use equation number 90, okay, remember decay constant lambda must be in per second. Therefore, the half-life, okay, if you are using equation number 90, must be in second. Okay, to get lambda in per second, you need to use T half-life in second. Okay, so that's why we need to do a conversion unit for time. Okay, so basically these are the equations applied for the subtopic 9.2. Alright.